Okay, so previously we have looked at resistors, and in general we worked with resistors which have a fixed resistance. So for example here we've got a resistor with a 10 ohm resistance, and what that's telling us is that this resistor has a constant fixed resistance of 10 ohms no matter what you do to it. So what we can actually do is plot a graph of current against potential difference across this resistor, and what you notice is you get a straight line. And this graph is actually common to lots of different components which we call ohmic components. So an ohmic component specifically is one that obeys Ohm's law, and Ohm's law we have actually seen before. That is the V equals IR equation which we saw previously, and Ohm's law specifically is saying that the resistance is constant, and if the resistance is constant then what we are saying essentially is we have this relationship where the voltage and the current are proportional to each other. That is, a potential difference and the current are proportional, and therefore you get a straight line when you draw your current potential difference graph. Now it is important to note the relationship between the gradient of this line and the resistance. So because we've plotted current against potential difference, the gradient here is actually equal to 1 over the resistance. Okay, if you were to plot it the other way around, you get the gradient as being equal to the resistance, but in this case we get the gradient being equal to 1 over the resistance. But nevertheless, because it is a straight line, we can tell that the resistance is constant and it does stay the same. Now we can also extend this idea to non-ohmic conductors. So previously we said an ohmic conductor is one that obeys Ohm's law, where the current and the potential difference are proportional to each other as a result of the resistance being constant. So for non-ohmic conductors, the resistance is not actually constant, so the resistance varies, and we can actually look at specifically some examples of non-ohmic conductors which we should be aware of. So the first one is lamps. We also have diodes, we also have thermistors. Remember, thermistors, their resistance varies, and we also have LDRs, or light dependent resistors. So all of these are examples of non-ohmic conductors because they don't obey Ohm's law and their resistance, as we mentioned, does vary. So once again we can draw the IV characteristic. So the IV characteristic is what we drew over here, but we can draw it for a non-ohmic conductor as well. And specifically we're going to look at a bulb or a lamp. What would the IV characteristic for a lamp look like? So let's draw it out. So once again we're going to put current on the y-axis and potential difference on the x-axis. And previously we said that if it's an ohmic conductor, it would just be a straight line through the middle. So instead of having that, we're going to have essentially a curved line at the beginning, then it goes straight, and then a curved line at the end. And what you notice is that at very high currents or very high potential differences, it starts to behave in a non-ohmic way. But in this middle section here, this is basically a straight line and looks very, very similar to our ohmic conductor, because it does actually behave like an ohmic conductor in the middle section, and it is only at the ends that it starts to behave differently. So let's actually take a look. Why does it behave slightly differently? Well, what's happening here is when you reach very high potential differences or currents, you have a high temperature. Okay, and a quick note here, we do have a negative section to this graph, and the idea is this shows the direction that the current or the potential difference is in, or the polarity, but nevertheless the actual magnitude of the current and potential difference is very high at both of these sections. Okay, so the idea is that when you have very high currents or potential differences, you end up getting a very high temperature. And why does this actually impact the resistance? Well, if you imagine what the resistance actually is telling us how difficult it is for the current to flow. So if you have your wire here is made up of lots of particles, and when the temperature increases, what happens to these particles is they're able to vibrate and move a lot, so you get a lot more motion in these particles. And the reason why that is a problem is, if you remember before when we were discussing electrical current, it essentially is these electrons trying to flow through the wire. So these electrons, they try to flow through, but if your particles now are moving a lot more, this actually prevents the electrons flowing through very easily. They're going to bump into these particles a lot more. It makes it a lot more difficult to flow through. So what's happening is you're giving these particles more energy when you increase the temperature, and therefore what that is doing is it is increasing the resistance. And that is as we expected if we look at the gradient. So remember, the gradient is proportional to 1 over the resistance. Essentially it is 1 over the resistance. So as the gradient decreases, we're saying that the resistance has increased. You can see here the gradient becomes more flat. That's saying that the resistance is larger at these points. Okay, so that is the IV characteristic for a lamp. And we can also take a look at a IV characteristic for a diode. So again, a diode, like we said for the lamp, is an example of a non-ohmic conductor. And so the only thing we can say is that it's not going to look like a straight line because the resistance is not constant, and we would expect some of the gradient to change at some point. So let's once again draw our IV characteristic out. So current and then potential difference. And for a diode, if you remember, a diode specifically only allows current to flow in one direction, and in the other direction, if you try to make current flow, it has a very, very high temperature. So what that does look like on an IV characteristic essentially is something like this, where when you have a current flowing in the wrong direction, in this case the negative direction, there's pretty much no current allowed. And then once you get to the right direction, then you see basically a straight line, and the diode behaves as we expect, where it only allows current to flow in one particular direction. And in the other direction, you have a very, very high resistance. So in this section, very high resistance. So you can see here, even when you have a negative potential difference, it doesn't allow the current to go negative. So now let's look at another component, the thermistor. So the thermistor is another one of our non-ohmic components. And essentially the way a thermistor works is when the temperature increases, what happens is the thermistor is designed to actually decrease the resistance. Okay, so it has an inverse relationship, the temperature and the resistance. In fact, if you were to look at this on a graph of resistance against time, then it would look something like this, where this is your resistance, and sorry, not time, but temperature. And essentially what you notice is as the temperature increases, your resistance would decrease. So it would look something like this, and the exact curve will depend on the nature of the thermistor you have. But essentially some applications of thermistors are things like circuits, which are useful to be controlled by temperature. So things like fire alarms, if the temperature gets too hot, then the thermistor will actually decrease its resistance, might allow a certain voltage or current to flow, and that will trigger the fire alarm. Things like a thermometer itself, so you could have an electrical thermometer, and therefore the reading on the thermometer would be based on how much current is allowed to flow through the circuit, and again you could use a thermistor for that purpose. The last thing we can look at is a light dependent resistor. Light dependent resistor on LDR. So the way a light dependent resistor works is when you have a very bright light, you increase the brightness. What happens to the resistance is it actually decreases. So again, you have this negative relationship between the brightness of the light and the resistance. The brighter the light is, the lower the resistance, and the darker it is, the higher the resistance. And these are very useful when you want to control a circuit depending on how bright or dark it is. And so for example, if you're trying to control streetlights, they are made up of light dependent resistors. And what happens is the light dependent resistor, when it gets dark, the resistance increases. That might draw enough current or potential difference in another part of the circuit to trigger the lights being switched on. So those are the components we need to know. But finally, we will take a look at actually how to measure resistance. We do need to know, generally speaking, if you have a component, how do you measure the resistance of it? So we'll just take a filament lamp and you'll have a circuit set up like this. So you remember, we need a source of potential difference. So that will be our cell, and we can connect this up to our lamp over here. And then we want actually an ammeter, so we're going to place an ammeter in here. And remember, an ammeter we connect in series, and we'll go into more detail about series and parallel in a later video. But essentially you have your ammeter connected like that and your voltmeter connected like this. So your voltmeter is connected across the component, and your ammeter in this case can be connected anywhere in the circuit because it's a single loop, and so the current is the same wherever you put it. And so what we could do is we can switch on our circuit, and we can measure the current over here, and we can measure the voltage over here. But the problem then is that we only have one reading of current and voltage. So actually we want to get several readings to enable our experiment to be more accurate. And so what we can do is place over here a variable resistor. And remember, the symbol for a variable resistor is a resistor with an arrow going through it like that. And so the idea is now that we take a measurement for the current and the voltage at a certain resistance, so let's say 10 ohms. We then switch our variable resistor maybe to 20 ohms, and we measure it again, and then we might switch it again to 30 ohms, and so on and so forth. And that is one method of measuring the resistance of a component. Could be any component. In this case, we used a lamp. And remember, with our IV characteristic, if you want to plot the IV characteristic, you could also reverse the polarity. So we know that this is the positive and negative terminals of our battery or our cell. So instead, what we could do is basically just reverse the connections. So this could be connected this way, and this could be connected that way. You can see what I'm talking about. You could reverse it over here at the lamp as well. But essentially, using that, you can get the full range of results for whatever component you have. Okay, so hopefully that was useful, and let's get on to some questions now. And just a few questions to finish off, then feel free to pause the video and have a go. Okay, welcome back. Let's go through the answers. So question 1, is a lamp an ohmic or a non-ohmic conductor? Well, we said a lamp is actually an example of a non-ohmic conductor, even though it does behave as an ohmic conductor in the middle section of its IV characteristic towards the end. Then when the temperature increases, it does not. Question number 2, in an ohmic conductor, the current stays the same, the potential difference can never be negative, or the resistance is constant. Well, in an ohmic conductor, it obeys Ohm's law, where the voltage is always proportional to the current, and therefore we have to say that the resistance is constant. And question number 3, in a thermistor, the resistance increases when A, it gets darker, B, it gets hotter, or C, it gets colder. So a thermistor is linked to temperature, and if you remember, the resistance of the thermistor and the temperature have a negative relationship. or a negative correlation. And so essentially whenever it gets colder, the resistance of the thermistor would actually increase, and therefore when the temperature increases and it gets hotter is when the resistance of the thermistor decreases. So it is actually C over here. And question number 3, in a thermistor, the resistance increases when does it get darker, hotter, or colder? Well, the thermistor is linked to temperature, so it's not going to be A. It's not when it gets darker. That's to do with a light-dependent resistor. But a thermistor, the resistance actually increases when it gets colder. Okay, so the resistance of the thermistor and the temperature have a negative relationship or a negative correlation. And so what that means is that whenever the temperature increases, the resistance will decrease, and vice versa. Whenever the temperature decreases, the resistance increases. Okay, so hopefully you got those questions right, and I'll see you in the next one.